Hi, I'm Jill Gerke, a graduate student here at The Ohio State University. I will be discussing my paper, The Mid-IR Impact of Dust-Enshrouded Stars in 6 Nearby Galaxies, posted by myself and Gerke Kochanek on astro-ph. In this paper, we use archival Spitzer IRAC 3.6 and 4.5 micron data to identify AGB stars in 6 nearby galaxies. We are looking at the impact dusty stars have on the spectral energy distribution of a galaxy. A galaxy's SED is often modeled using stellar population synthesis models, meaning the stars in each phase of stellar evolution must be understood. However, due to the relative rarity of AGB stars, their contribution to these models has been difficult to calibrate. In this study, we identify dusty stars throughout a galaxy and measure their contribution in 3.6 and 4.5 microns, and look for trends with galaxy properties. In Figure 1 of the paper, which you can see here, shows the Spitzer image of M33, one of the 6 galaxies we study. The solid line outlines the area we define as the galaxy, and the dashed line marks the regions used to determine the background corrections. For the 4 more distant galaxies, we determined the total galaxy luminosity and performed PSF photometry within a similar region. The same general process was used for the SMC and LMC using the SAGE catalogs. To identify the mid-IR sources we found in each galaxy, we used the color magnitude diagram that you can see here. The y-axis is the absolute 4.5 micron magnitude, and the x-axis is the 3.6 minus 4.5 micron color. Normal stars with little dust are shown in blue, the AGB stars are shown in green, and other dusty luminous stars are shown in red. We sum the emission from each type of source and correct for background contamination. Uncertainties were determined using bootstrap resampling. We can now compare the amount of emission from each source type with the total luminosity of the galaxy. We can look at how the contribution from AGB or other dusty red stars varies from galaxy to galaxy and look for trends with galaxy properties. Figure 4 from the paper displays these results. The y-axis is the fraction of the mid-IR emission from the galaxy that is attributed to dusty AGB stars. The x-axis of each of the 4 plots displays a different galaxy property. We look for correlations between AGB fraction and galaxy luminosity, stellar mass, specific star formation rate, and metallicity. The 3.6 micron fraction is labeled with the galaxy's name and plotted with an open circle, while the 4.5 micron AGB fraction is plotted with a solid circle. We see there is a reasonable trend in each of these 4 plots. However, these properties themselves are also correlated in our sample of galaxies. There should be no strong correlations of the AGB fraction with galaxy luminosity, stellar mass, or current star formation rate. So the most likely interpretation is that the correlation is with metallicity. The dependence of the AGB dust production and the resulting IR emission on initial metallicity is not well understood, though our data supports increased dust production and mass loss rate for lower metallicity AGB stars. Figure 5 from the paper displays the bright red stars' contributions to the galaxy's luminosities as a function of their properties. For these sources, which are a mixture of massive stars and young stellar clusters, we expect a trend with specific star formation rate. If we exclude the SMC from our sample, we see an increase in red star contribution in the galaxies with higher specific star formation rate. It is possible we are seeing the effects of truncated dust production in the SMC due to its low metallicity. Overall, dust emission from AGB stars represents 0.1 to 0.8% of the bolometric luminosities of the galaxies, and ranges from 0.6 to 5.6% of the 3.6 micron emission. For more details, see our paper. Thank you.